Hi, so welcome back to this lecture where we will learn about Poisson distribution. It's a distribution that we have sort of touched upon before already. While we were doing the assignment, there was a problem on it, and we've said that how binomial distribution can behave like a Poisson distribution under certain conditions. That condition is, I've repeated that problem really, or what we've done in that assignment here, but we will come to it. So Poisson distribution is a distribution in discrete random variable, and it's probably the most important distribution, well, insofar as, its usage in probability and in statistics. And so let's just look at what would be a Poisson distribution. This is the definition of it. As I said, it's a distribution in discrete random variables. So a discrete random variable x with a spectrum like this, okay, that's a discrete spectrum, okay. It's infinite, but still, it's countable because you can count the elements here, 0, 1, 2, 3, 4. They're listed. It's countably infinite set, this spectrum, okay. So it's a discrete set. So a discrete random variable x with a spectrum like this is said to follow a Poisson distribution if its PMF, the probability mass function, is given by this particular formula. Probability that x takes the value k from here, from this spectrum, is given by this particular formula, where lambda is a parameter, okay? And it's called a rate parameter, okay? We will come to why it is called the rate, but for now it's just a parameter. And if a random variable follows a Poisson distribution, then in symbol, this is written like this, okay? X follows Poisson with parameter lambda, okay? And we've seen, how different random variables can follow different distributions with various parameters. For example, the Bernoulli trials had a parameter of p, or the probability of a success. The binomial distribution had two parameters, n and p, the number of Bernoulli trials and the probability of success there, p. So this is going to be what would be a Poisson distribution, okay? If you find a random variable, discrete random variable with exactly this formula for its PMF, then that would be called, then x would be said to follow a Poisson distribution with parameter lambda. And this is what we have already done before. So what we've said in the assignment, the problem that we had in the assignment, and also we've solved it, is that if you have a binomial distribution, let me call that y, it's again a discrete distribution but with a finite spectrum. So if you have a binomial distribution with n and p as the parameters, so the spectrum of y in this case would finish at n. So it starts with 0, 1, 2 and it finishes at n, okay. If you have a binomial distribution such that n is large, okay, n is very large, n is, or in approximate terms we say that n reaches infinity, n tends to infinity, but p is small, okay, the probability of a success in each of its Bernoulli trials is very small. But however, there is a condition. This is big and this is small, yet the product of these two must be a constant, okay? So the rate at which this increases is the rate at which p falls, okay? You can think about two sequences like that. So if the product is a constant, but still this one is big and this one is small, then we said that this PMF, the probability of this, the probability mass function of y, which is a binomial distribution, would tend or would start to behave like, will act like the probability distribution, probability mass function of a Poisson distribution. So if you're going to find under these conditions where n is large, p is small, but the product is a constant, if you wanted to find the probability of this, for this binomial distribution, if you wanted to find the PMF, that what is the probability that y is equal to k, then you could rather find the probability that x is equal to k using the Poisson formula, okay? And the answers will be approximate. That's what it means, okay? Under this condition, the PMF of binomial distribution starts to behave like the PMF of a Poisson distribution. So if somebody asked you to find the PMF of a binomial distribution, you could say that you could find the PMF of the Poisson distribution and say that it is almost equal because this behaves like this under these conditions, okay? So that was the meaning of the problem, and we've shown how this happens, okay, by formula. So that's the connection between binomial distribution and Poisson distribution, okay? Now, let's just tell you when can you expect to have a Poisson distribution, okay? So we've learned about binomial distributions in detail, and binomial distributions, a random variable would follow a binomial distribution when there were Bernoulli trials involved in it, okay? For example, tossing a coin, okay? And each turn you could get a head or a tail or a success or a failure, and if you repeated that n times, those were the kinds of examples for binomial distribution. When can you expect, or in what are the examples of a Poisson distribution? Here I have two, okay? There are many more. I have two just to give an idea of when you can expect a random variable to behave like a follow-up binomial distribution. So you can expect that the number of trials is going to be very, very large, because that's what Poisson distribution or this particular statement tells you. When n becomes large in a binomial distribution, it starts to behave like a Poisson distribution. So let's give you an example. Suppose you have, you're going to calculate the probability that you're going to have, or let's say you have a random variable which sort of takes the values as the number of visitors, okay, that would show up at your home each day, okay? So let's say x here follows, x is the random variable which follows number of visitors, okay? Now, potentially, this could go on and on. Potentially, you could have 0 visitors, you could have 1 visitor, you could have 2 visitors, you could have 3 visitors, you could have, well, depending on how many people you know, or even if you don't know, you could have strangers turning up at your doorsteps. So, really, this spectrum, the values that x can take here are really infinite, okay? But even if you don't go to infinity, you can say that x will take values, up to the number of people that you have known. A person in their lifetime could know for a few thousand people, for example. So I'm just saying that x could potentially take up values from 0 to 1,000 people, okay? Of course, it's not likely that all 1,000 of them will turn up to somebody's doorstep, just given one day. That's not going to happen, but you could. I mean, potentially that chance is there, okay? So x can take all these values from 0 to 1,000, and that's a big number, okay? But, you could go on and on to infinity as well. So n here, so really this is going to be 0, 1, 2. So let's say I know 1,000 people in my life, and I can expect that maybe up to 1,000 people will turn up to my house given a particular day. Okay, so that's so this is for x to behave like a Poisson distribution. The number of trials, so to speak, okay, will have to be a very large number, and that's given from how binomial behaves like Poisson when n is large. Okay, so this has to be one of the conditions, that the number of possibilities for a particular outcome to happen is very large. Now, but what really is the probability that, how many visitors do you have at your house every day? Well, not many. So the probability of a visitor to your house per day is really very low, even though you may be knowing 1,000 people. Okay, so the number of potential visitors is a very large number, but the probability that you would have a visitor to your house every day is very less. Okay, so P, the probability of a success here, okay, is actually very small. Okay, that's what I mean. So in such a case where you can think of X behaving like a binomial distribution, but with n being very large and p being very small, okay, and so in such a case you can expect X to be behaving like a Poisson random variable. Okay, this may not be exactly a Poisson variable. It may not be exactly following a Poisson distribution, because you could limit the n. Technically, for Poisson, the spectrum should be up to infinity. But since I'm limiting my number of visitors to the number of people I have known in my life, let's say 1,000. So, but I mean, it's not exactly Poisson, but it's going to be behaving like a Poisson. So that's one example where you can expect the random variable for this situation to be acting like a Poisson distribution. Okay, it's the number of visitors to your house each day. Let's take another example. Suppose you have a group of n people. Okay, group of some people, say 20 people, 10 people. Okay, and you want to know whether some people have the same birthdays. Okay, then what's the probability of that? Okay, or how, what kind of a distribution would that problem follow? Okay, so this is the second example. The number of people with the same birthday in a group of n people, say, where n is fairly large. Okay, so let's take 10 people. There are 10 people in a room. Okay, and you want to know, for example, what's the probability that at least two of them have the same birthday. Okay, at least two of them. So there are 10 people, or if you want to, you can make this 20 people. So let's make this number a little bit more. So there are 20 people in a room, and what's the probability that at least two people will have the same birthday? That's another question. Okay, so really, if X here for this one, if X here tells you the number of people with same birthday, the number of people with the same birthday, what are those choices? You could have 0 people with the same birthday, so none of the 20 people have the same birthday. You could have one pair. You could have 2 people having the same birthdays. That is one pair. Let's just say number of pairs. Number of pairs of people with the same birthday. Okay. You could have, 2 pairs. You could have, like that. Okay. So potentially you could have 20 people. So really, number of pairs with the same birthday really means we have to find out how many pairs are there in 20 people. Okay, how many pairs of people are there in a group of 20 people? Well, that would be out of the. So let's investigate this problem. Okay, and we will let's solve this problem. Okay, we're going to solve this problem. And that would be a problem in Poisson distribution. Okay, so we are going to find out what's the problem. So let's just write down the problem. So here is going to be, so let's make this concrete. We want to find, find the probability of at least one pair of people with the same birthday with the same birthday from a group of 20 people, let's say. Okay, so in a room you have 20 people, you want to find the probability of at least one pair of people having the same birthday. Okay, so that's the problem we're doing. So how many pairs are there from 20 people? Well, you can choose 2 people from 20 people. How many ways can you choose that? So really you can choose that 20 choose 2 ways. Okay, so number of pairs from 20 people would be 20 choose 2. Okay, and that really is, those are the pairs, all the 20 choose C people. So how many are there? So that's just going to be 20, 19 divided by 2. So this is 10. So that's 190. So there are 190 pairs of people from a group of 20 people. Okay. So, and you have to investigate to find out whether at least one pair will have the same birthday. You will have to go through all the 190 pairs of people and see, check if they're having the same birthday. Okay. So one way you can do that is you can define random variables, for example. Okay. Let's say I define a random variable I j k. Okay, it's an indicator random variable. Okay, where say from the 20 people, 1, 2 of the 20 people that are there in the room, I pick the jth person and I pick the kth person from that 20 people, and I form this pair JK, and I check if they have the same birthday. If they have the same birthday, I give this 1. Okay, if they have the same birthday, okay, and I call it 0. This indicates it's an indicator random variable. In other words, it's indicating whether the jth and the kth person will have the same birthday, and I give it 0 if it's otherwise. Okay, if they don't have the same birthday. So, and this repeats for all the pairs. Okay, I have to make sure that here j is smaller than k. Because suppose I pick the 5th person, if j is 5 and k is 7, I pick this 5th person and the 7th person and I check their birthdays. I don't want to repeat that again by picking j as 7 and k as 5. That would be the same pair. Okay, so I want to pick only. So the way you can restrict that is by making one strictly less than the other. Okay, you don't want j to take 7 and k to take 5 again. Okay, also you don't want j and k to have the same number. You don't want j and k to be the same person number 5. In that case, you don't have a pair of people. You just have one person and you've picked him twice or her twice. Okay, so this is the number of random the random variable. I'm defining these indicator random variables for jk, where j is strictly smaller than k. Of course, they will go up to 20. Okay, so I have these many random variables. And how many are there? There are 190 of them. Okay, I'm choosing 190. So there are 190 such random variables. Indicator random variable, jk. I'm using j and k. Okay. Now here, to answer this problem, to figure out the answer to the problem, let's say I form this new random variable x, which is really the summation of I12 plus I13 plus all the I57 is in there. Really, basically all jks, all indicator jks, okay, where j is less than k, and they will have to be in this range. Okay, so let's take this random variable, which is the summation of all these indicator random variables. In that case, if the 5th and the 7th person have the same birthday, then this will register 1. If this 1st and the 3rd person don't have the same birthday, this will register 0. If the 1st and the 2nd person don't have the same birthday, this will register 0. Let's say 10 and 19 have the same birthday, this will register 1. So really, finally, it will count out it will count out how many pairs will have the same birthday. This will give you a number of pairs with same birthday. Is that clear to everyone? Because this really is counting the number of pairs with the same birthdays and discarding the number of pairs without the same birthdays. Okay, so this really is, x is the variable we want for this problem, because we really want to find the probability of at least one pair. So we want, this x really counts the number of pairs with the same birthday, and this is the all important random variable we want for us to answer this problem. So right, so let's just answer it. So what distribution is this? What distribution will x follow? X follows, well, as you can see, each of these, what we call the indicator random variables, they are actually the Bernoulli trials. Because each of an ijk, this indicator random variable for the kth and the jth people, takes only two values, success and failure, 1 and 0. Okay? So each ijk indicator random variable is actually a Bernoulli trial. But you just have to figure out what the parameter is. In other words, with what probability will you have the success, or the two people will have the same birthday? Okay, what's the probability of this success? That would be the parameter here for Bernoulli, if you remember. Okay, you can go back and check when we define Bernoulli. So the probability of the success will be the parameter here. And what's the probability of a success? If I take the jth and the kth person, what would be the probability that these two will have the same birthday? Well, j can have a birthday on any of the 365 days of a year. Let's just say there are 365 days in a year. So j can have any day as his or her birthday. We're not putting any restriction on it. But whichever date is the birthday for j, k must have the same day as his or her birthday for this pair to have the same birthday. So if j has its birthday on the 1st of February, k must have the same day as his or her birthday. So once you figure out the birthday for j, you're left with only one choice for k. So j really has 365 choices for to choose from, 365 options to choose from for its birthday. But once you fix that, once those options are exhausted, or one of those options are picked, k really has only one option to match with j's birthday. And how many possible such options were there for both of their birthdays? So 365 for j and 365 for k. So j could have had all 365 days as his birthday, and k could also have that. Okay, so the number of possible choices for j and k's birthdays would have been 365 square, which comes in the denominator. This is a classical probability definition. But the numerator comes out to be 365 for j. That's a possible number of choices that j has, but k has only one choice that is the same as j's. So this really is 1 by 365, and that's the probability of the success. That's the probability of two people having the same birthday. So that should be your p here. The probability of a success is 1 by 365. So each of them, I, j, k, will have is a Bernoulli trial with parameter 1 over 365. So this really is a summation. So it's a summation of, how many are there? It's a summation of 190. There are 190 such indicator variables. It's a summation of 190 Bernoulli trials, and each of them are independent and identically distributed. Of course, whether the 5th and the 7th people have the same birthday has nothing to do with whether the 19th and the 20th people have the same birthday. So they're all independent, and they're all identically distributed as a Bernoulli 1 over 365. So therefore, by our definition of what a binomial distribution is, this is x is really a binomial distribution of 190 Bernoulli trials, and each Bernoulli trial has a probability of its success as 1 over 365. That's p. Remember, binomial NP, n was the number of Bernoulli trials, and p was the probability of a success for a Bernoulli trial. Okay, so this is a binomial distribution, x, the one that we have defined to solve this problem. Okay, and now as you can see, this is a binomial distribution, but n here is fairly large. Okay, it's 190. It's a pretty big number. Okay, it's not infinity, but it's still a large number. And p is quite small. It's 1 over 365 is quite a small number. Okay, so you can think of n being a very large number, or it is approaching infinity, and p being a very small number, but n and p being whatever it is, it's 190 over 365. Okay, that's a pretty reasonable number, 190 over 365. Okay, that's slightly less than half. Okay, so right. So in this problem, therefore, since n is big and p is small, but the product is a manageable number, it's not a very small number, not a very big number, it's less than half, we can think of this problem sort of following binomial, Poisson distribution. It's kind of following a Poisson distribution with some parameter lambda. Okay, we have to figure out what this parameter is. Okay, we have to figure out what this parameter is. Well, and then we could approximately give you the answer for this problem by the Poisson distribution. So to answer this problem, the probability that at least one pair, will have the same birthday, that is probability that x will be at least 1, because x counts the number of pairs with the same birthday. This is the same as probability, as it's always the case. Sometimes it's better to find out 1 minus x equal to probability x equals 0. Okay, because here x greater than equal to 1 means all possible values from 1 to 190, because x can go up to 190. But it's better to find it at x equals 0. It's easier, and just subtract that from 1. And this would be, if I know that this is kind of behaving like a Poisson distribution, this would be almost equal to, not exactly, but approximately equal to 1 minus the Poisson formula for this p, for this x, okay, which is e to the power minus lambda. We have to figure out what lambda is. Lambda to the power k, which is 0 here, by 0 factorial. So that's just going to be 1 minus e to the power minus lambda. Okay, so to answer this problem, we can say that it is approximately equal to this number. Okay, the probability that at least one pair will have the same birthday from a group of 20 people will be approximately 1 minus e to the power minus lambda. So let's just figure out what lambda is and then we are done. Okay, so what would be lambda? We know how we thought of this as a Poisson distribution. We thought of this as a Poisson distribution because of this particular condition. Okay, this particular condition. That n was large, p was small, but the product was, it was it's a moderate number. Okay, it's a constant. Okay. Now, what's the and this we called this product was the product we called lambda, if you remember. Okay, so so let's just write it here properly. N is big, p is small. So binomial was starting to behave like Poisson under the condition that this product was somewhat of a constant number. Okay, even though n was big and p was small. But in this case, this turns out to be, we know exactly what lambda is. It's given by np. It's 190 over 365 for this problem. Okay, we know what this figure is. So binomial was starting to follow Poisson with lambda, which was given by np, if you remember, again, going back to the problem we had solved for the assignment. So lambda really is this value, 190 over 365. And so therefore, this answer, probability that you will have at least one pair with the same birthday, is approximately going to be 1 minus e to the power minus lambda, which is 190 over 365. That approximately comes to, I have worked this out, it comes to 0.4058. Okay, let's just write it up to the fifth decimal place. So that's approximately the answer for the problem. Okay. Now, if you really wanted to solve this problem as a binomial problem and not solve it like an approximate Poisson problem, the answer would have been. So this is solving this one. This answer comes with the assumption that x follows Poisson with parameter 190 over 365. What if you think of x following binomial, which is exactly what it was, okay? This was the approximation case, with the parameter 190 and 1 over 365. What would be the answer? This would really be the exact answer, and I've figured that out as well. That was going to be, if you do the same problem, if you're going to find the probability that x was greater than or equal to 0, this would be by the same formula, 1 minus probability x equals 0. But now I will use the binomial formula. This is going to be not almost equal to, but exactly equal to 1 minus, what's the binomial formula for this? It's 190 n choose k is 0, and that is, then the p here, 1 over 365 to the power, well, the 0, the same k here, and 1 q, which is 1 minus p, that is 364 by 365. Sorry, that's a 5. And this is n minus k is 190. So really, this comes out to be 1 minus, this is 1, and 190 choose 0. This is something to the power 0 is also 1. So this really comes out to be 364 over 365 to the power 190. Now this is a big calculation if this number is big as it is here, okay? And it's much better to find out e to the power something like a half, minus half here. It's slightly less than half. It's much easier to use or figure this out figure out this number in a calculator than to figure out 364 over 365 to the 190. That's the disadvantage of actually following the binomial formula, because if n here is very large, then calculators or even computers may not be able to handle these numbers sometimes. So it's better to give you an approximate answer where the formulas are much better to handle. And this, in fact, this is not so big a number, and my calculator could handle it. It came out to be 0.40622. I'm going up to the same 5 decimal places. So the numbers are, so the exact value for this is going to be this, but the approximate value by the approximate, distribution, Poisson distribution, was this. Okay, so and you can see that they match up to the 2 decimal places. There's only a difference of 1 at the 3rd decimal place, which is not that bad. Okay, so it's a pretty good answer. If you increase 20 people to say 50 people, then you can expect the answers to be even more, because then you have n even large. So as n becomes more and more large, binomial starts to behave like Poisson even more. So the approximation will be even better. Okay. So here is a problem which we have actually worked out completely, and it's a problem. It's a good exercise in Poisson distribution. So that really gives an idea of how important this distribution is. Most problems which could not be solved as binomial problems, or there are shortcomings in the formula because it's just too big to handle. Things can be done using this rather easy formula, okay? But approximately, of course. All right, so we'll just finish this here and take things forward in the next lecture. Thank you.